Okay, we're at County Bridge Project in Kingman County, Kansas, just a few miles east of Spivey, Kansas. This bridge was constructed by Reese Construction. We did the PDA testing back in December of 2021, so about 7 months ago, on abutment 1 where I'm standing, and on Pier 2. And this is great access for doing our seismic refraction survey. So we're going to lay a line out parallel to the bridge. I think we'll do one perpendicular to the bridge at Pier 2 as well. So we'll be able to get a good profile of the channel as well as at the substructures where we did PDA testing previously. Hi, this is Casey with Foundation Testing and Consulting. FTC performs a variety of deep foundation testing, primarily dynamic pile testing for driven piles and cross-hole sonic logging for drilled shafts. And we do that typically for bridge projects under construction. We're also implementing a database of our PDA projects. So our company's performed PDAs at over 120 Kansas bridge projects and well over 250 bridge projects in Missouri. So our work was completed with the PDA testing in December of 2021. Here we are on July 22nd, 2022. The bridge was completed earlier this year. And as part of our compilation of our database project, I was working with my son. And son, you want to tell him what your idea was?
When we were compiling the database, we noticed that the planned pile tip elevation and the actual pile tip elevation, there was a large discrepancy there. This could have been for a number of reasons, but we found that it was often related to a lack of subsurface investigation, or it could have been prevented by more extensive subsurface investigation. So this is when I asked my dad if there was, different ways to kind of characterize the subsurface profile, and that's when we started talking about seismic shear wave velocity profiling using surface seismic methods.
So taking that idea a step farther, I thought, well, what if we get good shear wave velocity profiles for the subsurface at a bridge we've already tested or we're currently testing, and see if we get good correlation with pile tip elevation, particularly in a weathered shale profile, where sometimes it's hard to characterize just how far the pile will penetrate the weathered shale profile below the alluvium into less weathered rock to get the required pile capacity for the bridge design. So the idea was, is there consistent shear wave velocity that corresponds to these typical pile section sizes and pile capacities? So that was the initial idea. So we have to extend our thanks to Gretchen Smouter with Geometrics. My son and I were at the Superpile Conference in St. Louis in June of this year, 2022. And I had met Gretchen years before at another conference, and so we started talking about our idea, and immediately Gretchen was willing to support our research. Right now we're just doing this for our own benefit, to satisfy our own curiosity. So we're doing seismic refraction surveys. Gretchen arranged to get us a geode system with 24 channels, so we've been using that with the seismic refraction methods. They've also got us another set of geophones, 4.5 hertz geophones, so we can do MASW. The geophones we're going to use today are 14 hertz. And she's been really great supporting this research. And she, along with Mike Ortega, the head of the rental department, has made all the detailed arrangements for us to borrow this equipment and see if we get these kind of correlations with pile tip elevation, shear wave velocity, and if we get even more detailed profile information, we may even be able to relate unit side friction and end-bearing capacity for the driven pile per our PDA test data with our result. That's our primary objective for this investigation. Then it occurred to us that there are certainly many other applications for seismic refraction surveys to either support the design or construction of bridge projects in particular. My son mentioned difficulty accessing all the substructures for a bridge during design. And a lot of these projects are in rural areas, and it even closed the bridge for a day to drill a boring through the bridge deck's problematic because it creates a 45-minute or an hour-long detour for local residents. So it's very difficult to get access in many locations for traditional geotechnical investigations. With seismic refraction, you're able to do offset shots from the end of your geophone line and actually image the channel in areas where you wouldn't have access for a rig. So in general, I think here in the Midwest, we're based in Overland Park, Kansas, but certainly I've been a geotechnical engineer for over 35 years, and we've seen that the geotechnical investigations for bridge projects tend to be rather conventional. And I think there's opportunity to utilize cone penetrometer testing with pore pressure dissipation, perhaps seismic cone testing, and certainly surface geophysical methods. Another problem we see with piling projects is sometimes the designers will anticipate having the pile tip in a dense sand layer, and really it's a sand layer with pieces of gravel that inflate the SPT blow counts. And I've seen on a number of jobs where the pile, rather than hanging up in that zone, continued on as if there was no increase in capacity, as demonstrated with the PDA, until the pile extended to bedrock, tens of feet lower than planned tip elevation. And then finally, I think certainly you could use seismic refraction and other surface methods for liquefaction assessments. There's several projects in Missouri that are in southeastern Missouri near the New Madrid fault zone. The bridges on main arteries are designed to withstand the seismic event from the New Madrid fault. However, there's a lot of smaller bridges that even the foundation's not designed to withstand liquefaction. And you might be able to find that you are able to extend the foundations just a little bit deeper at a small incremental cost, such that if there is the design seismic event, the foundations survive, and you simply have to rebuild the bridge superstructure rather than having to rebuild the entire bridge, particularly with the foundation. That greatly extends the timeline. So what we're going to go with here today is we're going to turn you back over to my son. He's in charge of the field collection methodology as well as the data reduction. I'm serving more as the project manager role. We're going to get all his results peer reviewed. We've done a number of jobs already. We've had the equipment for about 10 days. We are going out on jobs on the weekend when there's less traffic, and certainly when the construction crews are not working. It's been hot this year, so they've been knocking off for the weekend. And so we have great access for this study. We have great ground truth. We know hard elevations for the existing bridge structure. We're able to correlate those elevations to our survey line. And certainly we have the ground truth from the previous design phase borings and our construction phase dynamic pile testing. So here we go.
So here shows the video of the seismic refraction survey we performed on FAS 13. This survey had a total spread length of 168 feet. That day we performed a total of 9 shot groups. Each shot group included 5 stacked shots with a 16-pound sledgehammer and the Olsen Instruments strike plate. The shot groups were performed at increments of 42 feet, starting at minus 84 feet from the first geophone and ending at positive 84 feet from the last geophone. Here shows the plot that we were able to achieve by reducing this data and analyzing it. Here's the subsurface profile from the plans. It shows alluvium over shale. Now here are the PDI plots that we gathered by doing PDA at abutment 1 and pier 2. The PDI plots show transition from alluvium into highly weathered shale and then into less weathered shale. Now next we're going to overlay the PDI plots across the Plot-Tarifa plot that we were able to achieve by doing seismic refraction. And it shows a strong correlation from the shear wave velocity and capacity from the PDA test. We plan on following the same protocols using seismic refraction to find correlations with historical PDA data. We plan on finding these correlations at many other bridge sites, following the same protocols using seismic refraction and historical PDA data. We plan on presenting these findings in a paper or at a conference after having our findings peer reviewed.